Well, we're finally making it out of our 2.2 videos, right? We've been spending a lot of time really solidifying the ideas in there, and there's a reason, because those are going to keep coming back, right? So now here we are with 2.3, where we're going to now talk about higher order, right? Order higher than 2. We've been doing second order. That's what we've been doing, ODEs for a while now. Prior to that, we did first order. So now we're going to be able to talk about nth order linear ODEs, right? So remember, right, this y to the, not y to the n, y with the n in parentheses of x, right? That is telling us the nth derivative of y with respect to x. That's the shorthand notation. So that's the same as the nth derivative of y with respect to x, right? So here it's clear y is our dependent variable, right? X is our independent variable, so we're going to continue with that, which is what we've been doing. Y is a function of x, is our unknown function in this differential equation, which is, of course, homogeneous, right? Okay, homogeneous. And why is this a linear ODE? Well, it's an ODE because it's an ordinary differential equation, right? Y just depends on x, right? Y is a function of x, is our unknown function, okay? And it's linear, why? Because y and all of y's derivatives appear linearly. They are only multiplied by functions of x. That's our p naught of x, p1 of x, p2 of x, pn minus 1 of x, okay? And now, so we could have had this guy multiplied by some pn of x, right? So the numbering system is going to be different in different books. I'm just kind of using the numbering system where the subscript on the coefficient function, right? We've been doing constant coefficients, but now we're going to generalize not both order, but also theory for non-constant coefficient ODEs. So we're going up in order that where n could be, n could be anything, right? 2, 3, 4, 5, 6, 7, on and on, right? Okay? N can be anything. Order differential equation. When we specialize down to n equals 2, then we'll just have our second order non-constant coefficient ODE, so that will give us the theory for that. And when the coefficients are constant, then you pick up the theory for constant coefficient as a special case, right? So we could have had a coefficient function Pn of x sitting out in front of our nth derivative of y, but the standard form, kind of like what we saw before with first order ODEs, the standard form is to divide through by that so that the coefficient of this guy is just 1, okay? So the coefficient of your highest order term, whatever is multiplying that when it's in this nice linear form, you want to divide through by that coefficient so that the standard, the coefficient multiplying the highest order derivative is 1, okay? All right, and so y and all of its derivatives just appear as multiplying functions of x only, right? No crazy y squared, y primes, y double prime over y cubed, right? Okay, none of that. It's linear, right? In linear ODEs, there's nice theory. Okay, so we're upping the order, and we're upping the fact that our coefficients can be non-constant, okay? All right, so let's see. Now, we're only going to generally get nice solutions when we have constant coefficient equations, and that's why we spent a lot of time talking about those guys. All right, so let's write another idea that we want to go with, but man, that's a long equation to write out every single time we want to talk about it, right? Okay, it doesn't matter whether I write y of x or y prime of x, or y prime, or y, right, or y double prime, it all means the exact same thing, right? But that's a lot to write out, okay? And so, instead, what we've already seen, we can introduce operator notation, and now we can call L our linear operator. We can call L acting on Y this differential equation, okay? And so solving this differential equation equal to 0 is the same as solving L of Y equals 0. So what does L mean? It means take the nth derivative of the function plus multiply the n minus first derivative times this function, Pn minus 1 plus blah, 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 the whole way down the line, right? Okay, so L of Y is going to make it way simpler for us to just keep referring to this guy. So here we go. I'm just going to put the cap back on this before it gets worn out. Okay. So, let's look at a theorem that we're going to want to talk about. What about solutions of this homogeneous nth order linear differential equation for y as a function of x? Okay. And this guy is our superposition. We've already seen it in the case of n equals 2. But it says if I have now n solutions, right? So this is an nth order equation, and now I'm looking at n solutions, y1, y2 out through yn, as opposed to when we had second order and we only looked at 2 solutions, y1 and y2. So if I have n solutions, of my homogeneous ODE, L of y equals 0, and now I'm like briefly panicking that I never pushed play, so let me just push record. I'm recording, yay, okay. So if we have n functions that solve this crazy differential equation, okay, we also call this the homogeneous problem. The homogeneous problem, right? Because it's L of y equals 0, right? Everything involving a y is on the left-hand side. What are we setting it equal to? 0 homogeneous, right? So the homogeneous problem, then a linear combination, you've heard that word before, right? A linear combination. Well, what is a linear combination now of n things instead of just of 2 things? Well, yeah, you guessed it. You're already there, right? We're going to combine these guys linearly, which means we're going to multiply them all by constants and add them together, right? C1y1 plus C2y2 plus C3y3, right? The whole way out to plus, yeah, the last one, C sub n yn, right? So that's my linear combination. And a linear combination of those solutions, you get, what do you think? What do you think? What do you think the result is going to be? Yes. Also solves the homogeneous ODE. Right? The homogeneous ODE. Where, I guess we introduced the C's, so we should say what they are. Where Ci are real numbers, Ci are arbitrary constants. Okay? All right, let's show that that's the case. Okay, so we're gonna just prove this. I might put it in quotes because we're gonna kind of do it super quick. So what are we doing, right? Well, if we're trying to show that this linear combination solves the homogeneous ODE, then what are we trying to do? We want to know what is the operator L when we put in C1y1 plus C2y2, right? Well, I'll write out one more just so you can kind of see it, the whole way out to Cn, yn, right? So what is L evaluated at C11, right? What happens if I put, instead of the spot y, I put that big, long linear combination there, and then take the nth derivative of that, plus this function times the n minus first derivative of that, plus the whole way down to here, this function times the second derivative of all of that, plus some other function p1 times the first derivative of all of that, right? Okay, and so hopefully from what we've done with just n equals 2, you get the idea of what's going to happen here, right? That L of this stuff is what? It's, let me actually come down here. Instead, because the operations of differentiation and then adding, multiplying by a function of the independent variable, not the dependent variable, right? A function of the independent variable, and adding those things together because they behave linearly, right? That distributes, the derivative distributes across a sum, right? So we can say that this is the same as L of C1y1 plus L of C2y2, right? Plus L of C3y3 plus L of CNYN, right? That would be the same if we just plugged in each individual guy separately, which we did do when we did back to the second order. And then, since this is being a constant multiplied by our guy, and if we just put in a constant here with each one of these, right? Constants pull out of derivatives. If you replace y double prime with a constant c1 y1 double prime, right? You have c1 y1 double prime, right? That's the same as c1 times y1 double prime, yeah? Okay, and it's the same whether it's the n minus first derivative or the second derivative, right? It's the constant multiple rule, yeah? Oops, that's now its derivative, right? Okay, and so that same idea that the constant pulls out of the derivative allows us to say this is c1 times L of y1 plus c2 times L of y2, c3 L of y3. So we love this operator, linear operator notation, because we don't have to write all that stuff out, right? Yeah? But what do we know? Now what? Now what? So this is what happens if we plug this crazy linear combination into that differential equation in place of y, right? And we end up saying it's equivalent to this, which is equivalent to this. But what is that equivalent to? What is L of y1? Well, it would mean put a y1 right everywhere you see a y. But what do we know about y1? y1 is a solution of this. So what is L of y1? There you go. L of y1 is 0. It's y1 solves the homogeneous problem, right? So if I plug y1 in, take the derivatives, put all that stuff in there, right, I would get 0 because I know y1 is the solution. What about y2? y2 is also a solution of the homogeneous problem. So what is L of y2? 0. Beautiful. All right, here we are. All of these guys are solutions of the homogeneous problem. And so what do I get? These C's are constants. Everyone's multiplied by a 0. I get that L of that stuff is 0. And therefore, all of that stuff is a solution of the differential equation. Therefore, y equals c1y1. Looks like an E, sorry. c1y1 plus c2y2, c3y3, all the way out to cnyn, right, is a solution of Ly, of the homogeneous problem, right? So, there's no reason why that C looks bigger than the other C's. Okay, so if I have solutions, any linear combination of solutions is still a solution, right? Okay, and that's now true for nth order. And we had done it for second order, right? And you go back and look at the videos from when we did that, specifically by adding two functions together and then plugging it in, multiplying one function by a constant that we knew was a solution, then plugging that in, going through all those derivatives. And it's no different with lots more derivatives and being multiplied by functions of the independent variable. The linearity is what makes it work, thus linear operator, right? Okay, so let's see, now where are we? Okay, so what do we got, right? We've got infinitely many solutions, of course, to the homogeneous problem. The homogeneous problem, right? Because all the C's are arbitrary, right? Arbitrary constants. Now we have n arbitrary constants, and so obviously infinitely many solutions. Yes? Okay. So now let's get a little more general. You're getting scared out there, aren't you? Let's get a little more general. Okay? Let's consider the IVP. So we're generalizing from the OD. We're going from the ODE to the IVP, right? Okay? So let's consider the IVP for the non-homogeneous problem. Now we're going to talk a lot more about non-homogeneous stuff soon. Okay? Got a little peek into it with one of your homework problems of 2.1. We'll go back and pick up a lot more stuff from there soon and then move forward. But it's good to get a little peek. That's just non-homogeneous. Okay? So let's consider the initial value problem for the non-homogeneous problem. All right, well, what does that mean, okay? So let's write those words in math. And man, I don't want to write out that whole crazy thing, right? So instead of writing this entire thing right here, what am I going to write? L of y. That's what L of y is, right? L of y means create that combination for us today, right? It meant something different. In the previous video, L was a different operator when we were only doing second order, constant coefficient, right? Now it's this crazy operator for nth order, general, standard form, leading coefficient 1, linear ODE, non-constant coefficient, yeah? All right, so if it's a non-homogeneous problem, are we going to be setting L of y equal to 0? No, that's the homogeneous problem. What would we set that differential equation equal to once we got all the y stuff is on the left side? That's really what this is saying. All the y stuff is on the left side. So if it's a non-homogeneous problem, what would have to be on the right side? Yeah, some function of x, right? Yeah, can't depend on y. Can't be anything over here. Y depends on x, so it has to be some function of x. So we'll just say g of x, right? Yeah? So that's the non-homogeneous problem. Okay? Okay? So that would be the same as saying that equals g of x, right? And now we're non-homogeneous. Right? Way simpler to use L of y instead of have to keep reading out the differential equation, yeah? The general differential equation. So we want to get some general theory about equations that like this, because that's a pretty general equation, right? Okay, that's one of our goals. Okay, so there's the ODE, so what are the initial conditions, right? Okay, so now we need initial conditions. Well, we're used to having y at x naught is, well, I'll just use the book's notation here, so b naught. So b naught would be some given number that was the initial value, the solution goes through the point x naught, b naught. B naught is the y value, okay? And then we knew in second order we needed y prime evaluated at that same x naught, right? If it wasn't evaluated at the same spot, it's not an initial value problem anymore, it's a boundary value problem, and now we're in Math 440. Okay, so anyway, so we need a notation for what this guy is going to be, and so that's going to be B1 from B1. So this was our alpha and beta from before. But we're going to have more of them, so we don't just want to go like alpha, beta, gamma, delta, epsilon, whatever. We want something that helps us know that's the one that goes with the function, the zeroth derivative. This is the one that goes with the first derivative, right? And then we're going to need more, right? For second order, we needed 2. This is nth order. How many do you think we need? Good, n. So we're going to need a y double prime at x naught. We'll call that guy b sub 2, right? So these are our initial conditions. Okay, we're going to have n initial conditions, right? And this guy is our ODE. Okay, and those two guys, ODE plus initial conditions, is an initial value problem, right? So we need more, right? There'll be one on y triple prime. We're not going to write them all, right? Because that's the beauty of dot, 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 right? And what's the last one going to be? On what? What derivative? Well, think about second order, right? The last initial condition was on the first derivative, right? For second order problem, we needed 2 initial conditions. Add alpha, y at x naught was alpha, y prime at x naught was beta, right? So what's going to be the last one? Yeah. The one less derivative than the order of the problem, right? The n minus first derivative. And then this guy will be called what? B sub n minus 1, right? Okay? All right. So we've got our nth order, non-homogeneous, linear, non-constant coefficient, ODE, plus our n initial conditions, right? Where, what are the b sub i's? They are real numbers, and they're given, right? They're the conditions that you're given that you have to satisfy. So now, not only do you know a point you got to go through and the slope of the tangent line at that point, but a lot more information at that point as well. Okay. So, what can we say about this very general problem, right? Super general. Well, we have a cool theorem, okay? The theorem says this. You might have guessed, it deals with existence and, you got it, uniqueness of solutions. Okay? So what do we know? Let's call this the, put it in blue. Let's call this the non-homogeneous IEP. Right? It's this ODE plus these n initial conditions, right? Right, there's n of them because we go down to n minus 1 here and then we have a 0th one here, right? Okay. Okay, so let's consider the non-homogeneous initial value problem. All of that, where L of y, right? This is shorthand for this ODE, right? Okay. What does it say? If the coefficient functions, what are the coefficient functions? All of those functions multiplying the y's and the y primes and the y double primes, right? All of them. So p naught up through p n minus 1 of x, right? Because we have n of them, yeah? And we don't have a pn because we have it in standard form and we divide it through so that 1 is our multiplying constant for our highest order derivative, right? Now, we don't do that, let me just mention, when we're doing second order constant coefficients, right, ay double prime plus by prime plus cy equals 0, we don't put it in standard form. We don't divide by a, right, because it's generally easier to solve that quadratic equation without doing that. Yeah? Okay. But we could, and then we would still, those equations still fit within this theory, right? So the theory will still apply. Okay. All right, maybe I didn't need to mention that, explain it, but that's fine, we said it. Okay, so I need all my coefficient functions, that's these guys, and my non-homogeneous term, which is, good, g of x, right, the right-hand side guy, okay, once you move all the stuff with y's to the other side. If those guys are continuous, right, continuous functions, just like Calc 1 continuity, right, if they are continuous, on some interval I is an open interval, right? So it's open. Some open interval I, right? So what do? You look at each one of those functions, all those coefficient functions, and the right-hand side function. You gotta decide when things go bad, right? When am I not in the domain, right? When am I dividing by 0? All of those. When am I trying to take the root of something negative, right? Square root of something negative. All of those same things that you would do to look for continuity in domains in calculus, right? Okay. So for some interval I, and I has to contain x naught, right? So x naught is where you're going to assign your initial condition. It's any point inside some interval where all of these functions are continuous. Yeah? So here we could say x naught is an element of I. Okay? As long as your x naught is in the set, the interval where all of those functions are continuous, then what do we get? Woohoo! We're excited, right? Then there exists a unique, right? There is one and only one, right? There is exactly one solution, right? That is crazy. Okay. Solution of the non-homogeneous equation, L of y equals g of x. Okay? Now, again, if g of x is 0, then we've got uniqueness for the homogeneous solution as well, right? Okay? All right, we're just being as general as we can here. So this is the ODE, right? That's that guy, that big, long, crazy ODE, okay? Pretty general, right? There's just a unique solution of the ODE that also satisfies the initial conditions, okay? That's all of these guys, right? All n of these extra conditions, right? Furthermore, this solution exists throughout the interval I. Right? That's pretty crazy, yeah? Okay? So let's think back for a sec. This is pretty awesome, right? So just like first order linear, right? First order linear, we cover up all of this, yeah? Divide by P1, and you have y prime if we do first order linear, right? You guys are good at this, right? First order linear, right? Okay, so all of this is gone, divide by P1, and you're left with y prime of x plus p of x, which would be p naught divided by P1. Y is equal to q of x, which would be g of x divided by P1, right? Okay? First order linear, what do we know? We know that we determine when we have existence of unique solution just by looking at these two functions, the coefficient function and the non-homogeneous side function, okay? That's kind of awesome, and the same is true for higher order linear. So we know when a solution, unique solution to this equation will exist for y just by looking at the coefficient functions and the right-hand side functions and knowing where they're continuous. That's pretty awesome. You know it ahead of time from the equation, right? Think about our nonlinear stuff in first order, right? You got Picard's theorem, but you don't have guarantees, especially like this, that the solution is going to exist throughout the entire interval. Remember that little nonlinear problem we did, y prime equals y squared, right? We had blow up in finite time. Nothing looked bad about that problem, but as soon as you get nonlinear, then you don't get things like this, okay? So we know that this unique solution is going to exist on the entire interval, and it's only going to depend on where these guys are continuous. So you've got that ahead of time, which is huge, right? Know that ahead of time. Now, unlike first order linear ODEs, we could come up with a general solution formula for all functions, right, that satisfy this completely general differential equation. When we move beyond first order, even to second order, forget it. You're not getting that, okay? So now we've got to look at special cases and figure out when we can come up with solutions, right? Constant coefficient is one of those special cases where we can get solutions, and we now know all possible solutions for second order constant coefficients, right? All right, so we are not going to prove this theorem, woohoo, right? Okay, yeah, I know you're glad about that. That's a pretty tough proof, take a more advanced class. So let's see, what else? Let's go back then to see what this theorem guarantees us then for the homogeneous problem, okay? So back to the homogeneous problem. So let's write that. Okay, we're doing the homogeneous problem, and what are we doing? Yeah, this guy is 0, right? The homogeneous problem, written more concisely, L of y equals 0. Written out more, there's L of y, yeah? Okay. All right, I'm gonna erase this, we're good. So if I'm trying to decide like where I'm going to have a unique solution, I just look at these guys, I figure out, okay, where is the interval on which what's the biggest interval on which every one of those functions is continuous, and then I just have to pick an initial condition that's within that interval, right? And then I can go, and within that interval, I'm guaranteed existence of a unique solution. Okay, so now let's look at the homogeneous initial value problem. So what am I going to do? If it's the homogeneous initial value problem, then this guy is going to be 0, right? Yeah? Okay. You guys all good? All right. Well, this is nice that this is here, right? So we know, what do we know about this homogeneous problem? We know this right here. So if I superposition, we know that if we have n solutions, then a linear combination of those n solutions is a solution of the homogeneous problem, right? We have infinitely many solutions to the homogeneous problem, right? Okay? The big question is really, okay, well, That's a lot of solutions, right? Infinitely many is a lot of solutions, yeah? Okay? The big question is this all of them? Is there something we're missing? Or, if we create this expression, will that capture them all, right? That's the big question, right? The same big question that we had with second order, okay? Whoa, what was that? I better go check what that was. I'm not sure what was happening there. Hope something crazy isn't happening. Oh, nope, it's still running. Okay, maybe it's just telling me, speed it up there. Bring it on. Okay, is that what you're saying, Jim? What's our big question? Our big question is, does this, right? Okay, we'll call that, did I call it star? Maybe not. Well, maybe I will call it star. I don't know. Yeah, well, we'll just leave it at that. Okay. Does this linear combination contain all of the solutions? We know it is a solution. It's also a solution, right? But does it contain all solutions? That's our question, okay? So if it contains all solutions, we're golden, right? Okay, because then, if so, that's a big if right now. If so, therefore, it's the general solution, right, to the homogeneous problem, right? If we can justify that it would contain all solutions, then it's the general solution to the homogeneous problem, right? Okay? So another way to say that, so does this linear combination contain all solutions, i.e. another way to say that is, can every solution to our, what is this, nth order linear, what else, homogeneous, yeah, nth order linear homogeneous ODE, can every solution be expressed as a linear combination of the n solutions, y1, y2, out through yn. Can you just have any old n solutions and then slap constants around them and add them, you know, slap constants multiplying them and add them together and call it the general solution? Can you just have any old n solutions, or is there something special that has to be true about your n solutions? Okay, oh, I did call that star. I just couldn't even see it. Okay, I just didn't want to start calling it star and then not refer back to it. Does this linear combination star contain all solutions? So, i.e., can every solution to our nth order linear combination be expressed as a linear combination star of the n solutions, y1 through yn? All right, that's our question. Yeah. All right. Well, what will make that true? Jumping up to here. I'm going to leave this here for right now. So this will be true if we can satisfy any arbitrary set of initial conditions for the problem, for the homogeneous initial value problem, right? So if you can say regardless of the initial conditions that get assigned, regardless of what these B sub i's are, I can always satisfy all of these initial conditions, then no matter what, then I will have gotten I will have my general solution, because any solution would be able to be expressed that way. Okay? So what does that really mean? So regardless of the ICs, what does that mean? The B sub i's, so I'll just B0, B1, out through B sub n minus 1, right? Regardless of those, can we always find, what are we asking? Can we always find, well, what? Constants, C1 through Cn, right? Because that's what you're determining when you're applying the initial conditions, if you think back to what you're doing with second order, right? Can we always find constants, C1, C2, out through Cn, to satisfy the ICs, okay? So, well, what does that mean? All right, well, here, this guy right here, we know is y of x, right? So what is y at x naught, right? Well, remember, y at x is c1 y1 of x, right? When I say c1 y1, that's really what I mean. y1 is a function of x, right? Plus c2 y2 of x. This is just shorter than writing this, right? Plus the whole way out to cn yn of x. Yes? Right? So what is y evaluated at x naught? Well, I put an x naught everywhere I see an x, right? So I don't want this marker to dry up. So what does this equation tell me, right? That first initial condition, that would say that C1 y1 at x naught, evaluated at x naught, plus C2 y2 evaluated at x naught, plus C3 y3 evaluated at x naught, you getting it, right? Plus the whole way out to Cn yn evaluated at x naught, that's y evaluated at x naught, right? Yeah? What do we want that to be equal to? B naught, right? But then we got this initial condition, y prime at x naught. Well, in order to do y prime, right, evaluate y prime at x naught, we first need to know what y prime is. Well, what is y prime? Well, y prime, well, if I take this derivative, right, well, because of the rules of that would be the derivative of this whole thing, right? But derivatives are a linear operation, right? They distribute across sums and constants pull out, yeah? Right? And so if I'm taking that derivative is just c1 y1 prime plus c2 y2 prime all the way out to cn yn prime, right? And so y prime evaluated at x naught is c1 y1 prime at x naught plus c2 y2 prime at x naught plus c3 y3 prime at x naught all the way out to, you guys tell me, yes, cn yn prime evaluated at x naught. That's what y prime at x naught is, and what do we want it to be equal to? This given number b1. We getting this? We need to do one more? Okay, let's do one more. What's y double prime gonna be? Okay, y double prime, right? Yeah, we get that, right? Okay. So what is this initial condition going to give us? C1. So what are we getting here, right? This is saying the initial conditions are n equations and my C's are n unknowns, right? Okay. we'll write down this one, y1 double prime at x naught plus c2 y2 double prime at x naught plus c3 y3 double prime at x naught, right? Out to cn yn double prime at x naught, and what do we want that to be equal to? E2, right? And that's going to continue on and on and on until we get down to the last equation, the nth equation, and the nth equation will be, you tell me, c1, y1, n minus first derivative, right? Because we started with the function itself, the zeroth derivative, right? Evaluated where? Good, at x naught, plus c2, y2, n minus first derivative of y2, evaluated where? Good, x naught, plus c3, n minus first derivative of y3, evaluated at x naught, the whole way out to cn, n minus first derivative of the n function yn, evaluated at x naught, and what's that equal? B sub n minus 1. So here are our n equations and n unknowns, right? Okay? Yikes, right? Right? We already did this, right, last video, in fact, when it was second order, right? So like all of this is gone, all of this is gone, right? And we're just solving these two is equal to alpha and beta, right? And that is easy enough to solve. Two equations for two unknowns for C1 and C2, yeah? But now you have n equations and n unknowns. What? Right? I mean, that's awful, yeah? Okay? We have these, it's possible, right? We have n equations, we have unknowns, we still don't know. We might have no solution, we might have infinitely many solutions, we might have a unique solution, right? Okay? We know we at least have the right number of equations for that many unknowns, but we don't know whether we can actually solve for those guys, right? Okay? So the simple thing that we did for second order was so that you would kind of see the process and understand it in the simpler case where all of this stuff is gone, right? And it's just those two terms is equal to these two guys, yeah? And you saw that you could solve for C1 and C2, but there was a condition, right? There was a condition because we were divided by this quantity in order to solve for C1 and C2. That's the way it worked out, right? There was some quantity in the denominator, and we needed that quantity in the denominator not to be 0 for those C1 and C2s to exist, right? Well, the whole thing generalizes to much bigger ideas than that. Yeah, I heard you say Ronskin. Okay, yeah, that guy is involved. And really, at this stage, we're not going to completely pursue this, but since some of you do have some linear algebra experience, and some of you will have a lot more linear algebra experience soon, let's just talk about what this is here, okay? What this is, it's a system of equations and unknowns, but it can also be written as a matrix equation, okay? I have on the right-hand side a set of a vector, if you will, of numbers b0, b1, b2, down to bn minus 1, right? A column vector that has how many rows? N, because we're starting at 0. N rows, right? And one column. N rows, one column. Yeah? Okay? N rows, one column. And these crazy equations over here can be written as an n by n matrix, n rows, n columns. Okay? So there's n squared entries in here. Times another column vector that has n rows and one column, which is the set of unknowns, C1, C2, C3, down to Cn. And then what goes into this guy is all of the coefficients of those things, and if we know anything or remember anything, or will soon recall things about multiplication of matrices, this is an n by n matrix times an n by 1 matrix is an n by 1 matrix, then what goes across this top row here is these guys that are multiplying those guys. So we've got y1 at x naught, y2 at x naught, all the way out to yn at x naught, right? And if I think about that row, and I kind of turn it on its side, and it multiplies each one of those guys, and I add them together, and they equal b naught, and that's my first. If you don't understand that, don't worry about it right now. Okay. So what's my next row going to be? It's y1 prime of x naught, y2 prime of x naught, yn prime of x naught. Yeah? Okay? And all the way down to my last row is going to be the n minus first derivative of y1 at x naught, the n minus first derivative of y2 at x naught, out to the n minus first derivative of yn at x naught. Yeah? Okay. So that's a lot. Remember, these guys over here on the right-hand side are given. Okay? Those are our givens from our initial conditions. And this thing basically has the form of a matrix A, C equals B. Okay? And C is my unknowns, and this is my known right-hand side. And this is an n by n matrix, n by 1 column vector, n by 1 column vector. And we know that this system will have a unique solution. And that's what we were wondering, right? Can we uniquely solve for these constants, C1 through Cn? Can we uniquely solve for them to satisfy any set of initial conditions, right? And if so, then we've got our general solution back here. This system will have a unique solution for the capital C, which is the set of, sorry, I know you can't see this, the set of the constants, okay? So the C1 through C2, if and only if, all you linear algebra gurus out there, can you tell me? You're going to become a linear algebra guru soon. If not, so don't worry. You don't really need to have known this at all. It's not considered prereq material. We're going to get a unique solution for these if and only if what is true. The determinant of that coefficient matrix is not 0. Okay, the determinant of the coefficient matrix is not 0. But we've already talked about determinant for a 2 by 2 matrix, but what is determinant for an n by n matrix? Well, that's coming later as well. We're not actually going to compute these this way, but it's important to know the theory is there and it exists and it's intimately connected with so many things related to the ideas of linear algebra. Okay, so this system of equations can be rewritten this way, and what should we raise next? Maybe here. We're so close, we're so close. So what is in the A spot? It's this crazy matrix right here, right? Yeah? And the determinant of that matrix evaluated at x naught is kind of the deal, right? Okay? So we basically have a matrix, and we're saying, okay, well, looking at the determinant of a matrix that looks like y1, y2, yn across the top row, y1 prime, y2 prime, yn prime, right? y1 n minus first derivative, y2's n minus first derivative, yn's n minus first derivative. We're taking the determinant of this n by n matrix, right? And we want that evaluated at x naught, not 0. Yeah? Well, that determinant seems probably pretty useful. And so we call it something. What do you think we call it? The Wronskian of y1, y2, out to yn. okay, evaluated at x naught, okay? So the Wronskian, we looked at what the Wronskian of two functions were. This is generalizing the concept of the Wronskian of n functions. It's also computed by a determinant. Such determinants are nowhere near as easily computed as a 2x2 case, okay? So that's why you don't really need to be able to do that just yet. At some point in time we will talk about that. And so what have we discovered? Okay, here we are. Back to answering our big questions, which were there. Answering our big questions. So we've essentially arrived at the following theorem. Look at that, you didn't even know. How cool is that? Okay. So this theorem says what? Let's let all those coefficient functions be continuous. Okay? We're talking about the homogeneous problem now, so we don't have to worry about g of x. Okay? Let those be continuous on an open interval I, like somewhere from A to B, like minus infinity to infinity, okay? Negative 1 to 1, something like that. Okay. Open parentheses, right? So let's assume we have that, which we needed for our existence of uniqueness theorem, right? We need continuity there, and we need y1, y2, out through yn to each be solutions of the homogeneous ODE L of y equals 0, right? Okay. So we've got this non-constant coefficient. Cool, we're going to get theory for this. So what did we just say? Okay, based off of this idea, if it is the case that, maybe I'll just put the if down here. The Wronskian of our n solutions, right? Okay. In general, right, this thing is a function of x, right? Okay, so we needed to be able to solve that initial value problem assigned for a specific x naught, then we need to be able to say that the determinant of that guy evaluated at x naught is not 0, right? But the initial condition could be assigned at any point inside the interval I, and so that's why if we have the Wronskian not 0, okay, for at least one point, in I, then every solution to L of y equals 0 can be expressed it's getting sloppy now, right? Can be expressed by our guy star as a linear combination of those n solutions, okay? Every solution, so this is the general solution. Provided this is true, okay? For at least one point in the interval, okay? Now it's pretty cool though assign this initial condition at any point in the interval, right? At any point in the interval, and then be able to solve those equations for a linear differential equation, it's actually going to be the case that, well, not only is this Wronskian going to be non-zero at least one point in the interval, but if I've got the right set of solutions so that I generate the general solution, that Wronskian is going to be non-zero everywhere in the interval. Think back to those examples we were doing last time, right? When we were computing the Wronskian in a 2x2 case where the determinant is easy to compute, right? For second order, when we computed this Wronskians, wasn't it true that the determinant was never zero? It wasn't even that it wasn't zero at some point. It didn't turn out to be some function, right, that at least, you know, could be evaluated to not be zero somewhere. But it was just that the function, that what came out, that function was either strictly positive or strictly negative, never zero, right? That's a cool thing associated with solutions of a linear differential equation. That's not true about Wronskians in general, okay? So let's play out the rest of that idea and tie this back then to how this is now going to help us. I know what you're sitting out there saying. What's the point? Okay, well, the point is for you to understand that there's some serious theory behind all this. Then now, how are we going to start to use this to help us solve some higher order differential equations that are constant coefficient, where we can actually come up with the y1, the y2, the y3. As soon as we hit the non-constant coefficient, except for very special cases, those coming up with these guys, the solutions is extremely more challenging. Okay, so let's come back to here. So how does this tie into, last time we talked about, well wait, we had already talked about linear independence of two functions, and then all of a sudden the Wronskian showed up on the scene and saw that that was related to linear independence. So our next question becomes, how does that play into linear independence here, right? Where is this? So now you're like, but wait, how does this tie into the concept of linear independence? Independence and linear dependence. Right? How does that play in? And I would stop the video now and make a new video, but I kind of just need this, and so it's just simpler to just keep going. So you're tough, you can do it. We're good, right? Okay, so we need a definition. So I'm going to come over here and at least create more space for myself. Leave that down here because this is kind of the kicker of that. Okay, so we need to do the definition. We need to generalize our definition of linear dependence and linear independence because our definition held for two functions, right? So we say that y1, y2 out through yn are linearly dependent if and only if, here's the definition, the equation that's a linear combination of those guys, C1y1 plus C2y2 out to Cn set equal to 0 if that equation has solutions other than all C sub i's must be 0. Okay, so if that equation has solutions without having every single one of those C sub i's to be 0, right? If we make all the C's 0, then obviously the equation holds, right? But are there other C's where C's aren't 0? -5, 12, 1, right? That could make that guy 0. If so, that set of functions are linearly dependent, right? The solutions with not all C's 0, linearly dependent, right? Okay, and so if the only solution to C1y1 plus C2y2, C3y3, Cn equals 0 is all the C's 0, right? If the only solution is you gotta make them 0, then the functions are linearly independent on an interval. On I. They're linearly independent on I. This equation on all of I as solutions, right? Okay? So, it's exactly what the generalization you would expect, right? To go from 2, when it was 2, these guys were in here, right? Okay? And now it's n, and so there's no. Okay, well, if we look back here, then this equation, C1y1 plus C2y2 plus C3y3, right, that guy, if I get rid of evaluating, whoops, yeah, if I get rid of that, evaluating at an x naught, right, and set that equals 0, I have, then I've got that equation, yeah? So if that equation is true, right, this is my equation for linear independence, right? Linear independent if and only if all the CI's have to be 0, identically 0, right? But that's one equation for n unknowns, right? One equation for n unknowns. So what could I do? Well, if this equation holds, then I can take the derivative of both sides, right? And if I take the derivative of both sides, then this guy, the derivative of the left side is C1y1 prime plus C2y2 prime plus C3y3 prime, right? Okay, and the derivative of 0 is 0. And so, by getting rid of those guys and turning that into a 0, then I have that equation, right? And if that equation holds, right, on an interval, right, this all holds on some interval I, right, then so does that. And then I can take the derivative again, right? So I'm not treating these as numbers, I'm treating them as functions, yeah? And I want that to hold on an interval, and so I get that, right? And I can keep doing that exact same thing. And then I get down here, yeah? And now, instead of a non-homogeneous system of linear equations, I have a homogeneous system of linear equations where everything on the right-hand side is zeros, and on my left-hand side, I've just got my functions, yn of x. Yeah, okay, I just got rid of the x naughts. Yeah? And it's the exact same. So this was the actual equation for linear independence from that, we can create n minus one more equations because this has n unknowns in one equation, and that's not so useful. But each one of these equations has to hold if this guy holds, and that gives me n equations for n unknowns, and then I'm back to the very same type of thing, right? That now, instead, I've got an n by n matrix A, same n by n matrix A, but this time as a function of x, times my n by 1 constant vector of my constant with unknowns, but now it's equal to the 0 column vector. And again, if I have this guy, if the determinant of A is not 0, then what do I know? What do I know? Determinant A is not 0, right? If and only if the only solution to this guy is that the C has to be 0, right? So that's the whole block that would say, now the only way I can take all this stuff and set it equals 0, solve all those equations, is if each one of these guys is 0. C1 is 0, C2 is 0, C3 is 0, Cn is 0, okay? And so that's the exact same thing as the Wronskian not being 0 is going to force every constant to be 0, and therefore, because this is our first equation in that system, that's going to justify linear independence. Woo! That's super cool, super cool, super cool. But now, right, that's a lot of work to compute all that Wronskian stuff. Some of you have no idea how to compute an n by n determinant. Won't always be the case, but for now, you don't need to. So sometimes it's just way more work to do the Wronskian to try to test for linear independence than it is to use the definition for linear independence, okay? But the theory is there. There is a process. Everything we wrote down last time still applies. If the Wronskian's not 0 at some point in the interval, then the functions are linearly independent, right? The Wronskian's not 0, the functions are going to be linearly independent. The contrapositive of that says that if the functions are linearly dependent on the interval, the Wronskian will be 0, okay? Computing a Wronskian and finding that the Wronskian is 0 tells you absolutely nothing. So that's another reason not to use Wronskian all the time, because if all you're doing is looking for linear independence or linear dependence, if the Wronskian is 0, you know nothing. You've got to go back to the definitions. Now, also with the Wronskian, you got to have, like, the function has to be n minus 1 times differentiable as well, right? So maybe it doesn't even have a derivative, like absolute value stuff. Well, then you can't use the Wronskian. You got to use the definitions, yeah? What else? This idea down here then tells us also that same final ideas as last video. Regarding Wronskian and linear independence. Okay? But now with this piece that we just talked about, we know one thing we do know if the Wronskian is 0, the Wronskian of a set of functions is 0 somewhere, then what we do know is that these solutions, these guys, cannot be a fundamental solution set. To an nth-order linear homogeneous differential equation to, we'll just say L of 1 equals 0. Whew, that's a lot simpler than saying all that other stuff, right? So if the Wronskian is 0, you know you don't have a fundamental solution set, okay? And that's pretty cool. And if you do have a fundamental solution set, right, then the Wronskian is never 0. So that was onto positive, right, of this, and vice versa, right? Because that's what they are. Yay. All right. You ready to do one example that's a homework problem? Woohoo! And then we'll close this out? Yes. Okay, let's do that. All right, so what's the moral of this story? There's a lot, yeah? There's a lot of theory behind all this stuff, yeah? Okay? If you know some linear algebra, you can do a little more differential equations. And that's also going to be one of our goals later on as well. But also, you've got to understand where things come from and when to use them, how they're connected. You don't always just want to jump to Wronskian for computing, for determining linear independence, although it can be a super quick, super nice, super structured way to determine that, right? If it works, right? Right? If you go get the Wronskian to 0, then you're in trouble. If your functions don't have derivatives, then you're in trouble, right? Okay. But let's go look at an exercise. One of your homework problems. Then we're going to close this up. Exercise 2.3.10. So you'll see in the book, there's a lot of kind of ad hoc ways of trying to get at whether a set of functions is linearly independent or linearly dependent. So hopefully you're getting some more, a lot of different tools for attacking these types of problems, right? So the question is, are e to the x e to the x, and x squared e to the x linearly independent, and we'll add on minus infinity to infinity, on an interval, right? Okay? All right, so option one, okay, option one, based on what we just talked about, you could compute the Wronskian, right? What would the Wronskian of e to the x e to the x, and x squared e to the x be? Well, it would mean you'd have to know how to take the determinant of a 3x3 matrix. And this would be what you would put across the top, y1, y2, y3, right? Yeah? y1, y2, y3. And then this would be the derivatives, and this first derivatives, and this would be the second derivatives. Well, this column would be nice and easy. But these two columns would require product rules, right? Okay, we don't want to do that, yeah? So we're going to say, okay, no, let's use the definition. Yeah, let's use the definition. Okay. Better option. Definition. So what do? We consider the equation c1 e to the x plus c2x e to the x plus c3 x squared e to the x, right? Linear combination, y1, y2, y3, right? c1, y1 plus c2, y2 plus c3, y3 equal to 0, right? And we try to see if we can show, that c1 equals c2 equals c3 equals 0 is the only unique, right, solution to this equation. That's the question. If so, they're linearly independent, right? All right, there's a lot of different things you could do, right? We've talked about just plugging in values for x, right? Because this has to hold, again, right, for all x minus infinity to infinity. There's 3 equations, yeah? You plug in 3 different values for x, you're going to get 3 equations and 3 unknowns, and hopefully you can solve those and be able to show that 0 is the only solution, right? So there's ways that that there's a variety of other ways that your book explores as well. The Wronskian is another way, but might be more work here in this case. But what's one thing we could do here to make our lives a little bit simpler? Well, we know e to the x is always positive, so we could divide this whole equation by e to the x, right? It's always positive, we're not dividing by 0. What do we have? C1 plus C2x plus C3x squared is equal to 0. Yeah? So, showing this, dealing with this equation is equivalent to dealing with this equation. Okay, well now our question is, does this equation have only the 0 solution? Which incidentally would show that 1, x, and x squared are linearly independent functions, right? Yeah, beautiful. Okay, now there's a couple of things. So similar to what discussed in your book, what is this? This is the quadratic equation, right? ax squared plus bx plus c, right? So now we're saying that this quadratic equation, ax squared plus bx plus c, has to be equal to 0, right? For all x minus infinity to infinity. Well, what do you know? A quadratic equation has at most 2 roots, right? 2 zeros, yeah? Or has exactly 2 roots. Has 2 real roots, right? At most 2 real roots. And we've explored this equation quite a bit, right? With our repeated root and complex conjugate roots, yes? Okay, so is it possible for this equation to be equal to 0 for all x, infinitely many x, right? When it's a quadratic equation, when I can have 2 roots, right? Okay? 2 places that make it 0, but this has to be 0 for infinitely many. The only way that's going to be possible, because this is a quadratic equation, is if C1, C2, and C3 are 0, right? So we can kind of immediately get that. If that is a little scary for you, then you can just plug in some values, right? Okay, well how about x equals 0? Okay, if we plug in x equals 0, it has to hold for all x, right? What do we get? Immediately the C1 is 0, right? Okay, well then let's plug in x equals 1. Well, if we plug in x equals 1, we get C1 plus C2 plus C3 is equal to 0. Well, what do we know? We already know C1 is 0, right? So really we get C2 plus C3 is equal to 0. Now let's plug in x equals -1, right? And again, I'll keep it there. C1 plus, not plus this time because we're plugging in x equals -1, right? So minus C2, right? X equals -1 squared plus 1, so plus C3 is equal to 0. But what do we know? C1 is 0, because we already figured that one out from our earlier nice choice. So now we have these 2 equations, right? 2 equations, 2 unknowns. If we add them together, what do we get? These guys cancel and I get 2C3 is 0. And if 2C3 is 0, then what has to be true? C3 is 0, yeah? And if C3 is 0, and I plug that back into this equation, yeah? Then that gives me C2 is also 0. Now I have all 3 are 0, yeah? Okay, now that's a lot of this. But as long as whatever you do, you can justify and make it convincing to me that you understand what you're doing and how you're making your conclusion, and that you can argue what it is that you're doing to justify the conclusion, right? Therefore, we have these guys are linearly independent, okay? So, yes, right? Not only are they linearly independent, so are 1x and x squared. You can imagine how that all generalizes. I think that's enough generalizing for today. See you soon.